hope the crowd in the class is not too overwhelming for everybody. Again, I think people are feeling better. This is another wave of COVID, and we'll deal with it. The good thing is, thanks to Alina, we record all the lectures so that it's available, so they're available to everybody, so they don't need to be nervous about not being here. It's not the end of the world. The main thing that people have to do, and I'm glad this is on recording, is to take care of their health. That's number one thing. And you can always see the videos afterwards. And again, you can always ask me questions from the videos. Even if you see it on the video, you're welcome to either email me questions, or we can talk over the phone, or we can make an appointment, or we have office hours. I said, I'm available. I think we said Tuesdays at 5 with my typical office hours. Tuesdays at 5 o'clock, if I'm not mistaken. And also, I get here a half hour before class. So, are there any questions? All right, well, we were looking at transfer functions for various types of systems, and we were examining various combinations of systems. So, for example, when we looked at the transfer function for delay of theta seconds, we had e to the minus s theta. Just a little reminder. And then we started to look at systems in series. And if we looked at non-interacting systems in series, that's where the jth system only depends on what comes before it, the j minus first, not the ones afterwards. And we saw that was pretty simple, that the total g tilde, if I know the g tilde of each of the individual systems, then the total g tilde is just the product of the individual g tildes. And for example, when we looked at the response to a step function, what we saw was that if we have one CSTR in series, the output of the nth one versus t looks like 1 minus n exponential. But the more and more I put in series, we see as long as the total tau stays the same, if I just break it up into more and more CSTRs in series, that the curves start to look more and more like a plug flow reactor, And this was at least the situation without reaction. You can do it with reaction, but it's a little more complicated. But here the point was, you end up getting something that's closer and closer to a step, because in one CSTR, everything is well mixed. What comes in is well mixed with everything else in the reactor. When I have multiple CSTRs in series, I only have mixing in each CSTR. And if I have so many CSTRs in series, each one is almost like a cross-section of the plug flow reactor. So even physically, it starts to approximate the plug flow reactor. When we looked at interacting systems, that's where, and the simplest example was the tanks, where the heights of the tanks were related to each other because they were connected by a tube where the liquid could flow between them. This is just a simple example. Obviously, interactive systems can be much more complicated than that. I could have CSTRs where the outputs get recycled, for example. But in this particular system, obviously all of them are dependent on all the others. So we just take a simple system where there are only 3 tanks, where n is equal to 3, and we do that because if we solve for y1 and y2, we'll get a quadratic in the denominator, because we came up with this by taking the ddt of y1 and the ddt of y2, and each one of those gave me a linear, a 1 plus st in the denominator. So we only kept it to 3, so that way I would only get a quadratic in the denominator that I could solve. If I did it with 10, then I would have a 9th order polynomial, which I wouldn't be able to solve. I could factor it, but it becomes much more complicated. So we said once we have this g tilde, now g tilde for y2 prime over x prime is this quantity. So this quantity in the square bracket is g tilde of how x prime affects y2 prime. This is 2. And this square bracket is how g tilde how y3 prime affects y2 prime. And we know that both of these have the same denominator. And we saw that for questions of stability, What's important are the zeros of the denominator, because we recall when I have a g tilde of s, that's n tilde of s over d tilde of s, a numerator over denominator. And if they're both n tilde and d tilde are polynomials, then it's the zeros of the denominator, which we call the poles of the ratio. The zeros of the denominator give me the stability. And the numerator, along with its zeros, has no effect on the stability, but it tells me about the actual trajectories. So it gives me the details of the time dependence are very dependent on the numerator, but not the stability. The stability only depends on the denominator. And we also noted that g tilde itself is very important for the response to a sinusoidal input. We saw that the amplitude ratio was just the magnitude of g tilde of I omega, evaluated I omega. So clearly the amplitude ratio requires the numerator and the denominator. And the phase lag phi was equal to the arctangent of the imaginary part of g tilde of I omega over the real part of g tilde of I omega. So clearly the numerator and denominator are important for the amplitude ratio and the phase lag, but for stability it's only the denominator. So at the end of the last hour, we were in the process of examining the denominator here. And what we showed at the end of the last hour was this denominator. That the roots of this denominator, which I could call theta 1, theta 2, were real and negative. And that was the last thing we showed at the end of the last hour. Now, what I'd like to do is examine something else. So let's notice that this denominator, if I know the roots, and we came up with expressions for theta 1 and theta 2 just by solving this quadratic. I'm not going to bother rewriting that again, unless I have to. We could write this as 1 minus theta 1 as, I'm sorry. Yeah. We could write this as 1 plus s theta 1 times 1 plus s theta 2. If we know where theta 1 are the two roots, then let's just write that and find it out. That's 1 plus s times theta 1 plus theta 2 plus s squared times theta 1 theta 2. So that tells me that this polynomial and this polynomial are equal, where I know what theta 1 and theta 2 are the roots from the quadratic formula here. And we can still learn something from these quite clearly. One thing we can note, theta 1, theta 2 is equal to T1, T2. And theta 1 plus theta 2 is equal to T1 plus T2 plus K1 over K2, T1. Because they're the same, have to be the same polynomial, the same quadratic. Again, you don't have to worry about writing everything down. We'll take pictures of the blackboard. You're welcome to, but It's more important, you're welcome to write as much as you like, it's more important to listen and ask questions if there's something you don't understand or that you're not following. Okay, so let's just notice that theta 1 minus theta 2 squared, just for fun, let's calculate theta 1 minus theta 2 squared. That's theta 1 squared plus theta 2 squared minus 2 theta 1 theta 2. Which is, and if I can, so what I can do is I can add and subtract for theta 1, theta 2. And if I add them, then this gives me theta 1 squared plus theta 2 squared plus 2 theta 1, theta 2. So this is theta 1 plus theta 2 squared minus 4 theta 1, theta 2. And let's see what that is. Well, theta 1 plus theta 2 squared is t1 plus t2 squared plus k1 over k2 t1 squared plus 2t1 plus t2 k1 over k2 t1. Where I just squared this quantity as this guy plus this guy. And that's, of course, theta 1 plus theta 2 squared minus 4 theta 1 theta 2. But theta 1 theta 2 is t1 t2. 4 t1 t2. And by the exact same algebra, theta t1 plus t2 squared minus 4 t1 t2 is just theta t is just t1 minus t2 squared. Just as I did it here. It's the same algebra from here that I combine this term and this gives me t1 minus t2 squared. And the rest just comes along for the ride. So what have we found here from this sort of just for fun? What we found is that theta 1 minus theta 2 squared is equal to t1 minus t2 squared plus a positive quantity, because everything here on the right is positive. So that tells me theta 1 plus theta 2 squared is bigger than t1 minus t2 squared. That says the difference between theta 1 and theta 2 is bigger than the difference between t2 and t1. Bigger than t1 minus t2. I put absolute magnitudes down because I haven't told you which one's positive or which one's negative. It doesn't really matter if I tell you that theta 1 is the one with the plus sign and theta 2 is with the minus sign, then I don't need the absolute magnitudes. Okay, so what does this tell me? This says the product is the same, but the difference is bigger. If the product is the same and the difference is bigger, just think of it this way. If I have, say, 20, if the difference is smaller, I would have 5 times 4 is 20. If the difference is bigger but the product is the same, it's 2 times 10, or 1 times 20. So what does that tell me? That tells me that if the difference is small, then the numbers are close together. If the difference is big, one gets bigger and one gets smaller to keep the product the same. Is that clear? Okay, so what that tells me is that, if I don't even have to write it, is that one of the thetas is going to be bigger than both t's, and one of the thetas is going to be smaller than both t's. Now, why is that important? Because the inverse is going to have an e to the theta 1t and an e to the theta 2t in separate terms. One of them is going to be bigger, one of them is going to be smaller. Now the bigger one means bigger, so the one that's more negative is just going to decay faster than e to the, so if I look at e to the t1, t over t1 I guess was it? So this would be t over theta. So I can have something that decays with a T1, something that decays, say, with a T2. And what that tells me and let's get a different color chalk, is that, okay, one of these is going to decay faster, but one of them is going to decay a lot slower. So this one might be theta 1, and this one might be theta 2. Now, if I have a bunch of terms, if I have a sum of terms, and some of them decay quickly, the one that decays the slowest is the one that determines the dynamics. So, because I'm going to have one of these that's much slower than T1 and T2, what this tells me is that the interacting system is more sluggish than the non-interacting system. And that's again because one of the thetas, because the difference in the thetas is larger than the difference in the t's. The difference in the t's, of the t's themselves would be the roots for the non-interacting system. So since one of the thetas is going to be much longer, a much longer time constant than any of the t's, and that's going to control the response of the system, the interacting system is going to be more sluggish than the non-interacting system. That is, it's going to take much longer to get to a steady state if, for example, you talk about the response to a step function, to a step input. Any questions on that? Questions? So that's an important concept that I did all this algebra for. None of it was really complicated. This is all algebra you can follow. It's not even calculus, it's just algebra, but it gives you an interesting result because you get to learn a lot about both the stability, which we did at the end of the last hour, as well as the dynamics of the system. Okay, so let's look at now non-interacting systems. With delays. Non-interacting systems in series with delays. So if I have a first order system, let's call them first order. So let's recall, a first order system has a G tilde of S of Kp I over 1 plus STI. And a system with a delay system, has G tilde of S of e to the minus S theta. And if I have non-interacting systems in series, then I get G total is equal to the product of the GIs. Tilde. So let's do this. So if I have, so what do I want here? So for this situation, G tilde is the product of a bunch of KPIs over 1 plus STIs. Different letter, J, and times a product of e to the minus S theta K. So what I'm doing is, here I have each of the first order systems. I have a bunch of first order systems, and I have a bunch of delays. So the delays, when I multiply them, just look like this. I multiply the exponentials. Now, I may have different number of delays than I do first order systems. So that's why I have a different subscript here. And actually, there's no reason to do this. I can just put that. I only need one index there. So let's notice what this looks like. I have the overall steady state gain, Kp. Kp is just equal to the product over all the first order systems and KPIs. Nothing unusual there. The denominator, this denominator, has roots minus 1 over T1, minus 1 over T2, minus 1 over Tn. As usual, this is the denominator. But the delay is equal to, well, let's notice that the product here, the product on K of e to the minus s theta k, well, the product of exponentials, you add the exponents. So that's equal to e to the minus s times the sum on K of theta k. So the total delay is equal to the sum of the individual delays. But I can do slightly better than that. Let's see how I can do slightly better than that. Well, notice, if you recall, if I have first order systems in series, these first order systems in series, I can think of them as CSTRs in series. And we know that CSTRs in series, if they're small, can eventually give me something that looks like a plug flow reactor, where a plug flow reactor is just simply a delay. So what does that tell me? Well, I can notice that e to the st is equal to 1 plus st plus st squared over 2 factorial plus dot dot dot. So that's the Taylor series. If st is small compared with 1, then this term, when I square it, is going to be much smaller than this term. If st is not small compared with 1, I can't do that. I can only do that if st is small compared with 1, because I want to neglect all the other terms. So this term is going to be small compared with st. So if it's a small number, then when I square it, it's going to be a lot smaller than when I started with. Okay, well, what does that tell me? That tells me that 1 over 1 plus sti is about equal to 1 over e to the sti if sti is much less than 1. And that's equal to e to the minus sti. So under this assumption, if that's the case, then I can write g tilde as the product on I of KPI times e to the minus s times the sum of the theta k's times a product of e to the STIs. So this is the sum on K. Times psi plus the sum on I of the PIs. And this is not equal to, this is approximately equal to, if all of the STIs are much less than 1. Now what does that mean, STI is much less than 1? That says that S is a small number. S being, and remember, S being a small number means I'm looking at the long times. S much less than 1 over Ti means long time. Because remember from the final value theorem, we saw that t goes to infinity of f corresponds to s goes to 0 of sf total. So what this means is that I'm dealing with long times, i.e. t much greater than all the ti's. So at least if I'm looking at the long-time behavior, it looks like I have a much longer delay. It looks like the total delay is equal to the sum of the theta k's, the sum of the real delays, plus the sum of the TIs, where the TIs are the time constants of the first order processes. So that's sort of an interesting result. Are there any questions on that?
What does that mean physically?
Physically, it means that, so let's imagine, so what do I mean by a series of first order systems of CSTRs and delays? So if you think of delay as a plug flow reactor and a first order system as a CSTR, so here's an example where I have a bunch of CSTRs and plug flow reactors. And so I have an X coming in here. And here I have a CAN coming out of the nth one of these. So what does this say? This says if I have an input versus t, let's have a step change in the input, t is equal to 0. And I want to look at CAN. And it would, let's say it was steady state before. So if I had just delays, if I'm dealing with long times, so times much longer than some of the TIs, then this sort of just looks like a step where this is the total delay. Now, if I look at shorter times, there might be something going on here. It's not just going to be flat like this, but the main jump is going to come at the end at the total delay that's equal to this. And what does that mean? Why is that? Because if there's a change here, it's not immediately felt at the output, because in between I've got these delays. And I've got delays at plug flow reactors, but even when I have CSTRs in series, let's say I didn't have the plug flow reactors. If I had a step change in here, it wouldn't immediately be felt here even without the plug flows, because the changes here then will feed changes here. And remember, if I have a step change in the first reactor, the next, which is a step change in the concentration, the outlet to the second reactor doesn't have a step change in concentration, it's a change in slope. And in the third reactor, it's a change in the second derivative. So in the nth reactor, it's only a change in the nth derivative. So that's much slower. It's not like you see the result from a change here immediately at the output. So that's why, because all of the other reactors, the first order systems in series, don't respond immediately. So as long as we're dealing with times long compared with the T's, the characters and time constants, which for CSTR with no reaction is just tau, just the space-time, then they seem to be like a delay. There's stuff going on here, but if we're only looking at long times of this size, most of the action comes at the end. Does that answer the question? Yeah. Other questions? Okay, well, as we said, if G tilde is a numerator over a denominator, again, the denominator completely determines the stability, but the numerator is important for the dynamics. So let's see exactly what that means. Let's look at, and we saw that in systems that were in series, say non-interactive is trivial, the roots don't change. The roots of the denominator of the whole thing are just all the roots of the denominator of the individual system. Even with interacting systems, we saw that even though the roots change from t's to thetas, the properties don't really change. It's still stable because the roots are still real and negative. And the only thing is it gets a bit more sluggish. So that's what we found. But let's look, for example, at parallel systems. So for example, let's say I have a G1 tilde and a G2. And let's say they're both first order systems. So G1 tilde is KP1 over 1 plus SP1. And G2 tilde is equal to KP2 over 1 plus S2. So that's sort of a simple situation. And this is and let's go through and calculate Y3 prime tilde. And here I'm going to need your help again, because you have to remember those rules that we had before. So how do I relate Y3 prime tilde to Y2 prime tilde and Y1 prime tilde? Can we please have a volunteer? I'm sorry? It's a sum. So Y3 prime tilde is Y1 prime tilde plus Y2 prime tilde. And what's Y1 prime tilde? How does Y1 prime tilde relate to, I should number these consistently. How does Y1 prime tilde relate to X1 prime tilde? Somebody else. Remember, your job is to look at your notes and keep up. We did this a week ago. What is the relationship between Y1 prime tilde and X1 prime tilde? Do I have to call on you? I will call on you if you don't volunteer. Y1 prime tilde is equal to X1 prime tilde. What happened to G2? Come on, we did this in class and everyone was able to do it then. You just didn't look at it since then.
Y1 prime is equal to X1 prime.
Yes. So this is equal to G2 X1 prime tilde. And, I'm sorry, let me number this appropriately. So that way it's G1. X1 prime tilde. And how about Y2 prime tilde? What is Y2 prime tilde?
G2 prime tilde times X2 prime tilde. G2 times X2.
X2 prime tilde. And what's the relationship between X prime, X2 prime, and X1 prime?
They're equal.
They're all equal. Good. So this is G1 tilde plus G2 tilde times X prime tilde. And I have Y3 prime tilde. So let's see what that is. That's equal to, so I have G tilde overall, which is Y3 prime tilde over X prime tilde, is equal to G1 plus G2. Is equal to KP1 over 1 plus SP1 plus KP2 over 1 plus SP2. Well, I need to combine them into one ratio so that it's in the form of N tilde over D tilde. It's a sum now, so I have to do the arithmetic or the algebra. So I write this as 1 plus SP1, 1 plus SP2. But now the numerator is KP2, 1 plus SP2, plus KP1, 1 plus SP1. That's sort of basic algebra. And I want to rewrite the numerator. So the denominator is not changing. So the numerator is going to be KP1 plus KP2 times 1 plus times 1, well, why don't we, so it's KP2 plus KP1 plus KP1 ST1 plus KP2 ST2. Where here I just multiplied out the 4 terms. And just for fun, I want to multiply and divide by KP1 plus KP2. And let's see what we get here. We have a g tilde of s is equal to. Now I can factor out kp1 plus kp2. And in the denominator, I have 1 plus st1, 1 plus st2. And in the numerator, I factor out kp1 plus kp2, so I have a 1 plus s times something. This is factored out. And this quantity here, kp1 t1 plus kp2 t2 over kp1 plus kp2. Well, let's see what kind of units does that have? If the kp's have the same units, then this has units of kp times t, this has units of kp times t, divided by kp has units of t. So this thing has units of time. So I'm going to call it t3. So what I have here is that g tilde of s with parallel structure looks like this. And now I have the same denominator I'm used to having for processes in series. Processes in series, I get products of these 1 plus st's in the denominator. But in the numerator, I now have a polynomial. So until now, I never had polynomials in the numerator. I only had constants. Now I have an n tilde. I have a numerator in tilde. And I want to notice a few things before going on. The first thing, by the way, can you guys see back there? Okay, so you have x-ray vision, you have telescopic vision. Okay, so T1 and T2 are physical time constants. They're physical, so they're positive. So for a CSTR, remember the T was related, if there's no reaction, to just the space-time, tau. And if there was a reaction, it also had contribution from the rate constant, if it was a first-order reaction, and from the rate constant and the concentration about which we were linearizing if it's a nonlinear reaction. So T1 and T2 are physical. So T1, T2 are both greater than 0 because they're physical. Now what about the KPs? KP is the steady state gain. Now the steady state gain, of course, depends on what my change is. If I change something to make the output bigger, the steady state gain in steady state is positive. On the other hand, if I lower, for example, let's say I have a CSTR and I lower the inlet concentration by a step, then the KP can be negative. So KP1 and KP2 can be either sign. Is that clear that a KP can be negative? Because if my inlet concentration of reactant goes down, if I introduce a step change, the inlet concentration goes down, then eventually the outlet concentration is also going to go down. So if it goes down, then the KP is going to be negative. We usually do examples where it goes up, but it can also go down. We've done both. Where, remember, we did cases where volumetric flow rate went up, and then later on it went down. So the KPs can be either sign. Since the KPs can be either sign, KP1 plus KP2 can be positive or negative. And therefore, T3 can be either sign. T1 times a negative number plus T2 times a positive number need not add up to something positive. Is that clear? That T3 is not really a time constant, it's a combination of time constants and KPs. So it has units of time, but it's not physical in the sense that it has to be positive. Clear? Okay, so what does that tell me? That tells me when I solve this system, so I look at, say, Y3 prime versus P. I could have situations, remember, so I now want to invert this. And actually, why don't we invert it for a step function before drawing pictures? We have our sheets. Please take out your sheets. So if I have a step, if x prime is equal to delta x times a step, theta t, then x prime tilde is delta x. What's the Laplace transform of a step function? 1 over x. So therefore, the g tilde I want to, or y prime tilde, is equal to g prime tilde, g tilde times x prime tilde, is equal to kp1 plus kp2 times 1 plus st3 over 1 plus st1, 1 plus st2 times delta x over s. So let me just circle the stuff that's constants that come out. These constants come out. So if I invert to get y prime of t, I have kp1 plus kp2 times delta x times something. So can someone tell me what line this I find in the table to invert this particular quantity? What line in the table? Does that look like 15? 15 only has 2 powers of s in the denominator. I have 3 powers of s.
10.
This is just reading.
10.
10. So line 10 is exactly of this form. Line 10 is of this form. So when I invert, I keep the constants I kept, and then I need to multiply that by 1 plus t1 minus t3 over t2 minus t1 times e to the minus t over t1 plus minus t2 minus t3 over t2 minus t1 e to the minus t over t2. So let's notice what happens here. At long times, so first of all, this is the effect kp1 plus kp2 is the effective, it's kp total. It's a total kp. And let's notice that at long times, both these, since t1 and t2 are positive, both these terms eventually disappear as expected. So at long times, y prime is just the kp total times delta x, because it's multiplied by 1, which is consistent with the definition of what kp is. It's the steady state gain. At steady state gain at long times, I should, delta y over delta x should just be kp total, which it is. But notice that I have quantities here where t1 minus t3 and t2 minus t3, they can be either sign. They don't have to be positive or negative. Same thing with t2 minus t1, they're differences. So in fact, the kinds of pictures I can get here are, I could of course get something that looks like this. But in addition, it's also possible, depending on what the numbers t1, t2, and t3 are, I could get something that looks like this, or something that looks like this. And let's discuss them for a second. Notice these two, the two in the middle, monotonically increase from the initial condition. In this case, why don't we make this y3? So this is y3 for t less than 0 to y3 at infinity. And let's notice these two increase monotonically. That they don't go to infinity and that they don't oscillate only depends on the denominator, on T1 and T2. But what they do in between here and here depends also on the numerator. And in particular, I can have somewhere in the middle that can go higher than y3 of infinity. This is called overshoot. Or somewhere in between, I might go down to a value that's below either the initial value or the final value, and that's called inverse behavior. Now, those things are really important. Why are they important? Well, let's say I have a tank, if I'm looking at the level of a tank. If I change the input and the steady state is a little higher, that's fine. But if in between I go much higher and the tank overflows, that's bad. Or if I undershoot, if I lower the input and at steady state, the height is a little lower, but somewhere in between the tank dries out, that could be very bad. Something can happen there. Or think of pressure. If I think of the pressure, if I make a change and the final pressure is below the maximum pressure for the thing to blow up, but in between it goes higher and the reactor blows up, that's really serious. Then people could die. The environment could be damaged. Lots of things, you could destroy the equipment. That's in the order of importance. So obviously, it's not like the numerator is unimportant. Even though the system can be stable in T1 and T2, it's still possible that you could have really bad things happening in between. Now, how can I get this? How do I get overshoot? Well, one way of getting overshoot is, remember, I have two processes in parallel. Well, it could be that one of them is fast and one of them is slow. If one of them is fast, meaning it has a small time constant, if the fast one, say, has a very positive steady state gain, so T1 is small, but KP1 is big. So initially, you only see the fast process. The slow process is still lagging behind. So this gives me a much bigger, this is trying to just do process 1. It doesn't see process 2 because process 2 is slow. So it goes up to KP1, which KP1, if KP2 is negative and T2 is big, so in this combination, KP1 is bigger than KP1 plus KP2, because KP2 is negative. So quickly, I go up to something close to KP1 over a time scale of T1. And then over longer time scales, T2, so this is T1, T2 over this time scale, the second process, the slow process, takes over and brings me down to KP1 plus KP2. Is that clear?
Can you go over it again, please?
Sure. So, how do I get overshoot? So let's imagine I have two processes here. Let's imagine that one of them is a fast process, that it has a small time constant, things happen quickly, and that one has a big KP, positive. And the second process, which is slow, meaning it has a big T2, has a negative KP. So the overall KP, steady state gain, is KP1 plus KP2, which, since this is negative, is smaller than KP1. So this difference is KP1 plus KP2. If the first process is fast and the second process is slow, initially I don't see the second process. I only see the fast one. So it runs up quickly KP1, which is a big number. Runs up way here. And then only over this longer time scale does the negative part come in and bring it back down to KP1 plus KP2. Okay. Now, the inverse of that is if I have inverse behavior. In an inverse behavior, I want the fast T1, which is small, to have a KP1 that's negative. So initially, the fast process, I always see the fast process and it's negative, not positive. And then I have the slow process, T2, negative, and a KP2 that's positive. And then over the long time scale, the KP2 takes over and goes back up. So here again, KP1 plus KP2 eventually gives me a positive number, but the sum is smaller than KP2. I never quite get all of KP2. Is that clear? Question? Okay, well, time flies when you're having fun. Let's now look at some block diagrams for more complicated systems. And let's get a bigger piece of chalk, so I still have fingers at the end of this. Let's look at a situation. What I want to start with. Let's look at a situation of a cooler, CSTR with a cooler. So let's get all the notation right. Let's call this theta cold in, theta cold out, and theta hot in. Let's see if there's anything else I want to do. Yeah, okay. So let's write out, first let's write out the differential equations for this, and then from that, we'll come up with the block diagram. So first differential equations, then block diagram. So differential equations. I've got rho v cv d theta c dt is equal to rho v cp times theta c in minus theta c. Plus UA minus UA times theta C is the plus, theta H minus theta C. So this is the flow in and flow out, and this is the heat exchange from the heat exchanger. Clear? So now let's divide out by rho v CV. And I'm going to let CV equal to CP. And I'm going to let tau be equal to big V over little v. So then I have d theta c dt is equal to theta c in minus theta c over tau plus UA over rho v cv tilde times theta h minus theta c. So all I did is I divided this out and relabeled, and then just broke the coefficients. And I'm going to let alpha equal to UA over rho v cv. So this thing is just alpha. And now I take the Laplace transform. Well, I'm going to bring this term and this term to the other side of the equation. And I have theta c tilde is equal to times s plus 1 over tau plus alpha is equal to theta c in tilde over tau plus alpha theta h tilde. So I took these two terms and I brought them to the other side of the equation. And here I should be working with the prime variables. So I'm going to work with the prime variables. So that, I'm working with prime variables so I don't have to worry about emission conditions. So let's notice that theta c prime tilde prime is equal to theta c prime tilde in over tau plus alpha theta h prime tilde divided by s plus 1 over tau plus alpha. S plus 1 over tau plus alpha. And I want to circle the guys that are Gauss transforms. Now I'm not solving this problem now. We've solved problems like this before. But what I want to do is I want to do a block diagram. So what I can see here is that theta c prime is the sum of two quantities. So I have theta c prime. It's the sum of two quantities. Well, I sum quantities by having them come together here. And one of those quantities came from theta c in prime. And the other one came from theta h. But I don't just take theta h and add it to theta c. They go through a box, which in this case is alpha over s plus 1 over tau plus alpha. It's this. And in this case, I get a box that's 1 over tau divided by s plus 1 over tau plus alpha. So I can represent this equation exactly by this block diagram. Is that clear? And each one of these guys is a g. This is the g for how theta c prime in affects theta c prime. And this is the g for how theta h prime affects theta c prime tilde. So we're going to, and again, diagrams help us do algebra much more easily and make it much less likely we're going to make mistakes. So being able to write a physical system like this corresponding to a block diagram is very useful. Why else is it useful? In about a week or so, I have to see, maybe I have the next class or the class after, I'm going to start to teach you how to use a program called Simulink. And Simulink is a part of MATLAB, which it's one of the sub-programs of MATLAB. And what it allows you to do is to make block diagrams. So it makes it very easy to make block diagrams. And what you can see is that this block diagram has exactly the same information that this equation has. And this equation, when I use my sheet here, can be inverted to get me theta c prime as a function of time. So all the information to integrate the equations to get the answer is in this block diagram. And that's sort of the key to what Simulink does. What Simulink does is it says, well, all the information I need to calculate the time dependence is in the equations, but I can represent the equations exactly by block diagrams. So if you input the block diagrams to Simulink, it will immediately give you the graph of the solution. So far we've had two ways of solving these problems. One is with the method of ordered differential equations. Two is with the Laplace transform. And three is let Simulink do it. That's what we're going to be able to do. But you still have to know how to construct the block diagram. And let's just construct a block diagram of something maybe a little bit more complicated. Let's look at the following system. So here we have a situation where, and I'm going to number them. Let's number the streams. So I've got 0, 3, so I've got a stream coming in with temperature theta 0. It gets heated up by contact in a heat exchanger with theta 4. And gets heated up to theta 3. Theta 3 goes into the CSTR. There's some sort of exothermic reaction here that gives me a theta 4 coming out. That's higher than theta 3. And that then is contacted with theta 0 to heat the system up. And what I'd like to do is I'd like to find the corresponding block diagram. So that's my goal for the next 10 minutes. So first, let's just look at the reactor. So the reactor, I've got rho VCV, the theta 4. Theta 4 is what comes out, so it's what's in the reactor, VT, is equal to rho VCV theta 3 minus theta 4. Plus minus delta H times the Rid constant, which is K 0 e to the minus E over K theta 4 times the concentration, say, some power, for example. The important thing here is that when I take, so I'd have to linearize this. So I'd have something, when I linearize it, I have something in terms of, so this is nonlinear. But when I linearize it, it's in terms of K4. So when I do algebra, I'm going to get theta 4 prime tilde in terms as something times theta 3 prime tilde. And that's it. Because this is going to give me something multiplied. But when I linearize this, this is going to give me something times theta 4. This is something times theta 4. They're all going to go to the other side of the equation, which is going to come in the denominator, and all I'm going to be left with is a theta 3, something times theta 3 prime tilde. So if you go through that algebra, so what does the reactor part tell me? The reactor is going to give me let's put it here. Reactor part is going to give me theta 3 prime tilde going into the reactor, and I'll have a G tilde for the reactor, and out will come theta 4 prime tilde. Is that clear? I don't even have to go through all that algebra right now. I could to determine GR, the G of the reactor. But from this equation, theta 4 prime tilde is only going to be in terms of theta 3 prime, something times theta 3 prime tilde. And this is going to have the contribution from the flow. So it's going to have the 1 over tau part, but then it's also going to have something from the reactor, from the linearization of the kinetics. Well, that's only this part. I still need to do, I also now need to do the heat exchanger. So let's do the heat exchanger. And if you remember, earlier in the semester we had a Q, the approximation for these heat exchangers was UA times the average of theta 4 minus theta 0 plus theta 4 minus theta 3 over 2. So this was the approximation that we had for the heat exchanger. Remember this, it wasn't a great approximation, but we said we would just take the UA times the average of the inlet and the outlet, the driving force. The driving force at the inlet is theta 4 minus theta 0, and the outlet is theta 4 minus theta 3, if this is the kind of heat exchanger where this is well mixed. Now, by heat balance, this is also equal to, this is heat balance. By heat balance, it's equal to rho V Cp times theta 0 minus theta 3. So this is the amount of heat transferred from here to here. So if the amount of heat transferred from this stream to this stream. So if I make it as a positive quantity, here it's a positive quantity, then I need to have theta 3 minus theta 0, because that's hotter. So I'm reasoning, just so I get the sign right, that if I'm transferring heat from here to this stream to make it this is hotter. So I've defined Q as positive, so because this is positive and this is positive. And then this has to be positive. Okay, well if those are equal, now I can try to solve for things. So if I want to solve for things, I have that Q, well, I don't need Q anymore, right? These two things are equal. So I'm going to divide through by rho V Cp. By rho V Cp. And I have a 2 here. And I notice that what I have here is 2 theta 4 minus theta 0 minus theta 3. So I've just divided through by this. And this is equal to theta 3 minus theta 0. And what I'd like to do is I'd like to get theta 3 in terms of theta 0 and theta 4. So let's solve for theta 3. Let's call this thing alpha. And I have theta 3 times alpha plus 1 is equal to 2 alpha theta 4 minus theta 0. What's theta 2? It's not theta 2, this is theta 0. Theta 3 minus theta 0. Plus 1 minus alpha times theta 0. Or I have theta 3 is equal to 2 alpha over 1 plus alpha times theta 4. Plus 1 minus alpha over 1 plus alpha times theta 0. So all I've done is algebra from here. And if I take the Laplace transform, I get those quantities. So what does that tell me? That tells me that theta 3 is equal to theta, something times theta 4 plus something times theta 0. I should be doing this with prime derivatives. Again, I should be doing this all with prime derivatives. So these are all prime. But what does that tell me? That tells me that the heat exchanger can be modeled as, I've got the theta 3 prime code is a sum of two quantities. So it's the sum of theta 4 prime tilde plus theta 0 prime tilde. Where in this one, I have 1 minus alpha over 1 plus alpha. And in this one, I have 2 alpha over 1 plus alpha. So here I've represented this equation by this block diagram, and now I put it all together for the whole system. And to put it all together, I want to combine this and this. So here I have theta 3 prime tilde. And here I have G reactor. And what comes out is theta 4 prime tilde. That's just I rewrote this. Now for here, theta 4 prime tilde has to go through a 2 alpha over 1 plus alpha. And it comes out as something that has to add to theta 0 prime tilde. Which then goes through 1 minus alpha over 1 plus alpha. And out comes theta 3. So here we have the block diagram that corresponds to this simple model of the heat exchanger. And the question is whether you can see it or whether it's too small. So why don't I rewrite it somewhere where you can see it. Can someone take a picture of this blackboard? Because I'm going to erase part of it. The person who's going to take a picture, just this blackboard right now. Or actually, I can just use this. I don't even have to do that. Never mind. Let me just do it from here. So, what I have, if I can see it, a mile away. Okay? So I have GR, so it's 4. This doesn't right. Okay, I guess we do have to do what take a picture. Were you able to take a picture of that blackboard? Is that a yes? Yes. Okay. So let's we'll call this blackboard 4. Let's just make copy of it over and make it larger. So I've got G tilde for the reactor. Comes out as theta 4 prime. What comes in is theta 3 prime. This goes through a box, which we said is 2 alpha over 1 plus alpha. And I have theta 0 prime tilde, which goes through a box, which is 1 minus alpha over 1 plus alpha. And combines and gives me this. And now what I'd like to do is come up with G tilde for theta, the overall G tilde. So let's go through and calculate theta 4 prime tilde in terms of G's. So in terms of the reactor, how do I write theta 4 prime tilde in terms of theta 3 prime tilde? How do I relate theta 4 prime tilde to theta 3 prime tilde?
G reactor.
So this is G reactor times theta 3 prime tilde. Now I want to relate theta 3 prime tilde to, let's call this theta A and theta B. So here I have two things that are streams that are coming together. So how do I relate theta 3 to theta A and theta B? Somebody else. How about right behind them? Some. Yes, good. Don't be shy. You know what you're doing, so just tell me. That's equal to GR tilde. And how do I write theta A in terms of theta 0 prime? I'm going to call this GA, and this one GB, so I don't have to keep popping them over. How do I write theta A in terms of theta 0 prime? Maybe behind him in the corner. How do I write theta A in terms of theta 0 prime? Don't just give it a shot. It doesn't matter if you get it right or wrong. You have to take your hand away from your mouth because I can't hear you. It's GA times theta 0 prime. And how about theta B? What's theta B? And what's theta B in terms of theta 4? Times? Yep. Don't be scared. You guys know this stuff. Don't be shy. So it's GB times theta 4 prime tilde. So now I have theta 4 prime tilde in terms of itself. So I have to write theta 4 prime tilde. I bring this to the other side of the equation, and I factor out and I divide. So this is GR tilde times GA tilde times theta 0 prime divided by 1 minus GR tilde GB tilde. So that tells me that the G overall here for 0 to 4, because at the end of the day, 0 is what's coming in and everything else is getting recycled. That's equal to theta 4 prime tilde over theta 0 prime tilde. Is equal to GR tilde, GA tilde, over 1 minus GR tilde, GB tilde. So we found for the as we solve for recycled systems, that we get a different denominator. And let me just emphasize something I've emphasized in the past. When you have recycled systems, systems with recycling, here that you have the heat being recycled. The heat is being recycled. Actually, I don't need this. So this system has now corresponded to this system. For the reactor itself, I had a G tilde that was just GR. For the reactor itself, I had GR. For the heat exchanger, I had a GA and a GB. I think I call it, is that the right order? This was GB. And this was GA. And each one of them has its own denominator. GA and GB have the same denominator, the 1 plus alpha. GR has its denominator, which we said has a contribution from the flow, 1 over tau, and a contribution from the linearization of the reaction. And each one of those denominators corresponds to what would be the stability if I only had a reactor. If I only had a reactor, or if I only had the heat exchanger. However, when I put them together in this system, I have a new denominator. I have 1 minus GR tilde, GB tilde. This is a different denominator. And remember what we said right in the beginning. It's the zeros of the denominator that determine the stability of the system. Since I have a different denominator, I have different stability characteristics. So it's possible that the reactor itself might be stable. The heat exchanger itself might be stable if they weren't connected, but when I connect them, I make it something that's unstable. And One thing that's happened over just let me finish the sentence on the answer. If you look at reactors that were built 50 years ago, energy was cheap. 50, 60 years ago, energy was cheap. And as a result, people didn't worry that much about doing things like this, about taking a hot stream and using it to heat a cold stream, because I could just turn on a furnace and do it. After the oil embargo of the early 70s, 1972 or 73, all of a sudden the price of energy went up, and people who were designing chemical plants said, wait, energy is expensive. We're not just going to throw the hot water into the river and kill the fish, and then turn on the furnace to heat a cold stream. What we're going to do is we're going to integrate, thermally integrate the plant, so that when I have a hot stream that needs to be cooled before I throw it into the river, and I have a cold stream that needs to be heated before it goes into the reactor, I'll put a heat exchanger there and do it. That's a great thing in terms of energy savings. The negative thing is if something goes wrong in one of those streams, it used to only affect that stream. Now it affects other streams because they're connected. So I've coupled the system. And these recycles give me couplings that mean a little problem here could cause a problem over there that could eventually feed back and increase the original problem. So I could get a vicious cycle. And that's how you can see physically how it's possible that even if the individual systems, this one or this one, are stable, that when I couple them, I could get something that's unstable because I could get a vicious cycle. So that's why the stability characteristics here are quite different from the original stability characteristics. And what you find is that this sort of tight integration of a plant, first of all, it makes things happen faster, because if I have a feedback, then that's going to increase the problem in this stream faster, because it was getting bad, but now it's getting pushed from the feedback to get even worse. And it makes the system harder to control. But you know what the attitude of the shareholders is, and the head of the corporation said, that's why we hire control engineers. We want to save money on the energy cost, so therefore, we're going to hire someone from City College who's going to do well in the control class to make it work. Question?
How is it possible to generate people they want unstable environment?
Is it possible when you combine them to get more stable? Yes, anything's possible. You can also, there are clever ways of doing the combination that make it more stable, but of course that just means we have to do the analysis. What we will get to very quickly, shortly, is now that we're experts in modeling, I'm going to give you another homework today. Now that we're good at the modeling, then we're going to actually talk about how to do the control. Now, just before, I know I'm 5 minutes over, sorry. As far as the exam, I graded the exams. I didn't give them, I want to give them back when only 10 people are here. But I'll give them back next time no matter what. Let me just make a basic comment. Before I give them back, I want you to note that absolute grades don't mean anything. What matters is relative grades. So your grade relative to the mean and the standard deviation. So don't worry about the absolute number. That's the first issue. The second the second thing I wanted to mention is that when you do an exam in this class or any other class, if you start to freak out, you're not going to do well on the exam. You need to be calm. Now, when I say calm, how do I know that people are freaking out? Because there are people that made mathematical errors that I know you know better. There are people who wrote things like the sum of AB, AI, BI, is equal to the sum of the AIs times the sum of the BEJs. You know that's not the case. That's obviously not the case. Let's say this is the average grade in the class. The average grade in the class is the sum over the grades, where A is the grades, and B is the fraction of students in the class that got that grade. So the sum of the fractions of students adds up to 1. So you're telling me that the average grade is just the sum of the grades? obviously. I know you know that, but if you're nervous, you're going to do things like that. So it's easy enough for me to tell you not to be nervous, but when you write down mathematical things that are obviously not right, that you know are not right, you're not helping yourself. It's better to think for a second. I'll have the rest of it next time. The other thing to mention is it turned out that problem 2 was a little longer than I thought. So what I did with problem 2 is I made part A worth the full credit and part B as extra credit. I did that in problem 2. So if you did good, if you did well on problem 2, you not only got full credit, you got extra credit.
Oh yes, I was gonna ask for the average.
I didn't bring it with me because I have them at home. But next time, I'll give them to you next time.